Imagine spending decades of your life and billions of dollars to hunt for a ghost. Not just any ghost, but a particle so bizarrely heavy it weighs as much as an entire atom of gold, yet so unstable it vanishes in less time than it takes light to cross a single proton. This isn't a movie plot. This was the reality for thousands of physicists in the late 20th century. Back in the 1970s, our map of the universe, the grand theory of everything we could see and touch, had a huge, undeniable hole in it. A final, missing piece to a puzzle of cosmic proportions. Without it, our entire understanding of matter and the forces that govern it was on the verge of collapsing. This is the story of the epic, high-stakes hunt for the most expensive particle in history, the top quark. For more than 100 years, ever since J.J. Thomson discovered the electron back in 1897, we've been on a quest to find the universe's fundamental building blocks. We smashed atoms, found protons and neutrons, and then we smashed those open, uncovering an even deeper layer of reality. By the 1970s, this relentless digging gave us a stunningly successful theory, the Standard Model of particle physics. Think of it as the ultimate periodic table. But instead of elements like hydrogen and oxygen, it lists the fundamental Lego bricks that build everything. You've got quarks, which build protons and neutrons. You've got leptons, like the electron. And you've got bosons, the particles that carry the fundamental forces. It's a beautiful, elegant, and powerfully predictive map of reality. And for a while, it seemed almost complete. Scientists had sorted the quarks and leptons into 3 generations, each one a heavier, more exotic echo of the last. The first generation has the up and down quarks that make up all the stable matter in our universe. The second and third generations are their heavier, unstable cousins, only showing up in high-energy collisions before disappearing in a flash. By the 1970s, physicists were on a roll, filling in the gaps in this map. In what's now called the November Revolution, 2 teams at once discovered the charm quark. A few years later, in 1977, researchers at Fermilab found the bottom quark. And just like that, the map had a very specific, very obvious hole. Quarks were supposed to come in pairs, up head down, charm head strange. So, the new bottom quark had to have a partner. A final, 6th quark that the theory demanded must exist. They decided to call it the top quark, finding it wasn't just about ticking a box. Its existence was critical. Without a top quark to complete that third family, the Standard Model would have some ugly mathematical problems. The beautiful symmetry of the theory would be broken, and our map of the universe would be fundamentally wrong. The mission was clear: find the top quark and prove the Standard Model was right. The hunt was on. There was just one tiny problem. Nobody had a clue how heavy this thing was. Early guesses were, let's say, wildly optimistic. But as experiment after experiment at accelerators around the world, including the powerhouse at CERN, came up empty, physicists had a dawning horror. They were dealing with a monster. The top quark wasn't just heavy. It was absurdly, titanically massive. This is where the expensive part of our story clicks in. Einstein's famous E=mc² is a two-way street. You can get a lot of energy from a little bit of mass, but you can also make a little bit of mass if you can generate a colossal amount of energy. To create a particle as heavy as the top quark, you needed to smash things together with more force than ever before. That meant building the most powerful particle accelerator on Earth. The stage for the final act moved to a sprawling lab outside Chicago, Fermi National Accelerator Laboratory, or Fermilab. There, they built the Tevatron, a 4-mile underground ring where protons and their antimatter twins, antiprotons, would be whipped up to 99.9999% of the speed of light before being smashed together head-on. It was a machine built for one main reason: to finally have enough raw power to create a top quark. Even with the Tevatron's insane power, the task was borderline impossible. See, the top quark has a fatal flaw that makes it the ultimate ghost: its extreme instability. The theory predicted, and we now know, that a top quark only exists for about 5x10^2 seconds. That number is so small it's basically meaningless. It's a billionth of a billionth of a billionth of a second. That is less time than it takes the strong nuclear force, the very force that glues quarks together, to even notice the top quark is there. It's the only quark that dies so fast it can't ever form a proton or a neutron. It lives and dies as a truly bare quark. So, how do you find something you literally cannot see? You don't. You hunt for its ghost. You look for the evidence it leaves behind. A top quark almost always decays in a very specific way, into a W boson and a bottom quark. Those particles then decay into other things: electrons, muons, neutrinos, and fiery blasts of particles called jets. It's this specific pattern, this unique cascade of decay products, that scientists had to find. It was like trying to prove lightning struck by studying only the sound of thunder and the pattern of singed branches on the ground. Inside the Tevatron ring, two giant, competing experiments were built to sift through the debris of these collisions: CDF, the collider detector at Fermilab, and D. And these weren't just machines. They were global collaborations, each with hundreds of scientists from dozens of countries, all wrestling with the same problem. Imagine these detectors as 3-story tall, 5,000-ton digital cameras. When protons and antiprotons collided in their hearts, they tracked the path, energy, and identity of every single particle that flew out. The amount of data was staggering. The Tevatron was creating hundreds of thousands of collisions every single second. But a top-and-a-top pair was only expected to show up in maybe 1 out of every 10 billion collisions. The teams at CDF and D had to design incredibly complex computer algorithms to filter this flood of data in real time, throwing away almost everything to isolate the tiny handful of events that just might be a top quark decay. It was the ultimate needle-in-a-haystack search, a monumental test of engineering, computing, and sheer human grit. The discovery, when it finally happened, wasn't a single eureka moment. It was a slow, grueling build-up of evidence. In October 1992, the first real clue appeared, a single event that looked tantalizingly like it could be a top quark. But one event isn't a discovery. It could just be a fluke, a random background event that happened to look like the real thing. For years, the teams refined their analyses. They got better at identifying the jets of particles spraying from a bottom quark, a key piece of the signature. Slowly, event by event, the evidence mounted. By 1994, the CDF team had collected enough data to submit a paper claiming the first evidence for the top quark, estimating its mass at around 175 gigaelectronvolts, as heavy as a gold nucleus. But the standard for a discovery in particle physics is insanely high. You have to prove, beyond a shadow of a doubt, that your signal isn't a statistical ghost. So both teams raced to gather more data, cross-check their results, and convince themselves, and each other, that what they were seeing was real. It was a time of intense competition, but also collaboration, as the two experiments pushed each other toward the finish line. Finally, on March 2nd, 1995, the two teams held a joint seminar at Fermilab. In front of a packed auditorium and the world's media, they announced their definitive, combined discovery of the top quark. The odds that their signals were just a random fluke were less than 1 in a million. The ghost had been caught. The hunt was over. The most expensive, most elusive, and most massive piece of the standard model was finally in place. For the physics community, it was a moment of incredible triumph and relief. The standard model, a theory built over decades of painstaking work, had held up. Its predictions were confirmed in the most spectacular way possible. Our map of the fundamental particles and forces was, at last, complete. But the story of the top quark doesn't just end there. In a lot of ways, its discovery is where the really interesting part begins. Finding it raised as many questions as it answered. For starters, why is it so ridiculously massive? Its weight, about 173 times that of a proton, is so out of whack with the other quarks that it feels like a cosmic clue. We don't have a good answer, but we know its enormous mass gives it a unique and powerful connection to another famous particle, the Higgs boson. The top quark's connection to the Higgs field, the field that gives particles their mass, is uniquely strong. This makes the top quark an incredibly powerful tool. By studying its properties with more and more precision, physicists can probe the Higgs field and hunt for tiny cracks in the standard model that might hint at new physics. Some theories even suggest that the top's extreme mass plays a role in the stability of our entire universe. It's no longer just the final piece of an old puzzle, it's a doorway to the next one. The hunt for the top quark was an amazing story of human ingenuity, global teamwork, and that relentless desire to understand our universe on the deepest level. If you enjoyed this trip into the subatomic world, hit that like button and subscribe for more stories from the frontiers of science. And let us know in the comments, what scientific mystery should we dive into next?